Given a rectangular prism, and we're required to find the total surface area of the rectangular prism, also known as a cuboid. So the total surface area of a rectangular prism or cuboid is given by the sum of the areas of all the lateral faces. So if we just look at this cube, this rectangular prism rather, we've got a front face and a back face. Right, so the area of that front face will be 8 times 5, so that's going to be the length times the height. So twice length times height plus. There's no particular, you don't need to learn the formula. There's no order. You just need to understand how to go about finding the total surface area of the rectangular prism. So there's a front face and a back face. So it's going to be 2 times length times height. So that's 2 times 8 times 5. We now also have a side rectangular face, 2 side rectangular faces, and that 3 is the breadth and the 5 is the height, so it's plus 2bh. So it's 2 times 3 times 5. Finally, we've got the top face, and we've got the bottom face. So that'll be length times breadth. And there's the bottom face and the top face. There's 2 of those, twice length times breadth. So it's plus 2 times 8 times 3. So if you look at this, it's 6 faces in total. We've got the top and the bottom face. We've got the 2 side faces and the front and back. And then we have a combination of all of those dimensions, the length and the breadth, the length and the height, the breadth and the height. So the length and the height, the breadth and the height, the length and the breadth. And now we just evaluate this. So 8 times 5, 40 times 2 is 80. 5 times 3 is 15 times 2 is 30. 8 times 3 is 24 times 2 is 48. 110 plus 48, it's 158. And the units will be centimeters squared. Shows solid A and the solid B. Solid A is made from a hemisphere and a cone with radius 6 centimeters. The cone has a sloping edge of 10 centimeters. Solid B is a cylinder with radius 4 centimeters and height 8 centimeters. The total surface area of solid A is equal to the total surface area of solid B. Work out the value of H and work out the height of solid A. Okay, so the total surface area of solid A is equal to the total surface area of solid B. So we need to establish a formula that expresses the total surface area of solid A and the total surface area of solid B. Let's start with solid B because it is a cylinder and it's very straightforward. So the total surface area of B, the total surface area is the top circular face and the bottom circular face. The area of each circular face is pi r squared, and since there's 2 surfaces, we'll have 2 pi r squared. And we also have this curved section here around the cylinder, and that is given by 2 pi r h. That's the total surface area of a cylinder. Okay, now the total surface area of solid A comprises, okay, so solid A is a hemisphere and a cone. Now, we need to just consider the cone and the hemisphere on their own first before we establish a formula for the total surface area of the solid. So if we just take the cone to start off with, total surface area of a cone is given by pi r squared plus pi rs. S is the slant height of that cone, and r is the radius. This is the total surface area of a cone on its own, okay? But in the context of the solid, right? Imagine we were painting a model of this ice cream cone, the solid A. We would paint around the cone like that, and we would paint this over here. But the circle is this circular face is inside the solid, which you clearly cannot paint. So we have to exclude that from the total surface area. The total surface area refers to the total exterior, the area of the total exterior area of that solid. So we need to consider in the context of the problem, the cone will not include that circular face. In other words, we will not be including this pi r squared. So the total surface area of solid A will only include the pi rs part of the cone. In other words, just that curved section there. Now the total surface area of a hemisphere, if we take a hemisphere on its own, circle, the total surface area, so that circular face will be pi r squared. And for a hemisphere, that curved section around the shape, the total surface area is 2 pi r squared. So the total surface area of a hemisphere is 3 pi r squared. But in the context of the problem, we are only going to be painting that curved section there, which is the 2 pi r squared. This circular face here is inside the solid, which we're not going to paint, right? So we're excluding that pi r squared. So the total surface area will just be, for the hemisphere part of the solid A, just the 2 pi r squared. So we're going to add the 2 pi r squared. This is now the formula for the total surface area of solid A. Now every problem is going to be different. You're going to have to take a composite shape like solid A and break it up into its components. Write down what the total surface area of those individual components are, and then accordingly determine what the total surface area of the composite solid would be. And it's going to be different with every problem that you get, so you can't memorize something. What you will need to memorize and remember is the total surface area, the formula for each basic solid, which you know because we've worked with all of those before. So we are now going to take the total surface area of solid A and equate it to the total surface area of solid B. So 2 pi times 4 squared plus 2 pi times 4 times h, which is what we're looking for, equals pi. The radius of the cone was 6, the slant height was 10, plus 2 pi times 6 squared. So just in terms of pi, this will be 4 squared is 16 times 2, that's 32 pi, plus 8 pi h equals 60 pi plus 72 pi. We can divide through by pi because pi is a non-zero constant. So 32 plus 8h equals 60 plus 72. We're dividing through by pi because we can, because it's a non-zero constant. It also simplifies your calculation. Instead of using pi, which is an irrational number, you'll avoid working with decimals, and it'll get messy if you start working with pi. So the fact that it's convenient to divide through by pi, we're going to do that. So 8h equals 60 plus 172. It's 132. 132 minus 32 is 100. H equals 100 over 8, which is 50 over 4, and that is 12.5. And the units were centimeters. Now I need to determine the height of solid A. So the height of solid A will be from the apex to the center of that circular face. So we'll call this, just to differentiate from this lowercase h, we'll just call that uppercase H. So this is a straightforward application of Pythagoras' theorem because of a right angle triangle. So 10 squared equals h squared plus 6 squared. H squared is 100 minus 36. H squared equals 64. Uppercase H will be the square of 64, which is 8. This is just the height of the cone. They want the height of solid A. Okay, so we've just determined the height. That H, uppercase H, is just the height of the cone. We also need to know what this height is here. The height of the solid extends to the bottom of the hemisphere. So we'll call this y, just to be different. That length y is simply just the radius, which I think we call uppercase R, is simply the radius of that sphere, which is 6. So the height of solid A is simply going to be uppercase H plus uppercase R, which will be 8 plus 6, and that's 14 centimeters. The diagram shows a solid made by joining a hemisphere to a cylinder. The radius of both the hemisphere and the cylinder is 6 centimeters. The height of the cylinder is 5 centimeters. Find the total surface area of the solid. Okay, so again, we have a composite shape here. We have a hemisphere and a cylinder. So we're going to write down the total surface area of each individual solid, the total surface area of the cylinder, and the total surface area of the hemisphere, and then we're going to determine an appropriate formula that describes the total surface area of this composite solid. Total surface area, we'll start with the cylinder, is given by 2 pi r squared plus 2 pi rh. This is for a cylinder, all surfaces visible. So by visible, again, pretend that we are painting a cylinder. We would paint the top circular section and the bottom circular section, each of which has an area of pi r squared. So that's the 2 pi r squared that we see there. The 2 pi rh is the area of that curved section. But now in the context of the problem, if we were to paint this model, this composite solid, we would paint the external area of the sphere, and we would paint the curved section of the cylinder, and we would paint the bottom, because that's what the solid would be sitting on. But we will not be able to paint this in a circular face, because it's inside the solid, so we won't be able to paint that. So to find the total surface area, of the solid will be one less circular face, so it'll be pi r squared, but we are going to be painting the curved section, which is 2 pi rh. Okay, so that is the part of the solid that comprises that comes from the cylinder. Now we're going to determine the total surface area of the hemisphere. So if we had a hemisphere just on its own, we would have that circular face, the area would be pi r squared, and this curved section here has an area of 2 pi r squared. Within the context of the problem and the solid that we're looking at, we would paint that curved section over there, which is 2 pi r squared, but we wouldn't paint this inner circular face because it's inside the shape. So the total surface area of a hemisphere is 3 pi r squared, but in the context of the problem, we are only going to be painting the curved section. So we will not be painting that pi r squared. So we're going to add 2 pi r squared. So this is the hemisphere part, and that pi r squared plus 2 pi r h is the cylinder part. Now, because the radius of both the hemisphere and the cylinder is the same, 6 centimeters, this r is identical. So we can add pi squared to 2 pi squared. So we'll have 3 pi r squared plus 2 pi rh, and now we can just plug and play. 3 pi times the radius is 6 squared plus 2 pi times 6 times the height of this h. Remember that this h came from the cylinder, and the height of that cylinder was 5. There'll be 36 times 3 is 108 pi, plus 30 times 2 is 60 pi, and that will be 168 pi. They want the answer in terms of pi, so this is how we leave it, and this will be centimeters squared. The diagram shows a shape made from a triangle JKL and a semicircle diameter JL. JKL is an isosceles right angle triangle, as you can see, because JL is 12.8 centimeters and so is JK. JK equals JL equals 12.8 centimeters. Calculate the area of the shape and the perimeter of the shape. Okay, so the area of the shape, again, there isn't going to be a formula for composite shapes. Composite shapes we break down into individual component shapes for which we know the area formula for. So the area of this shape will be the area of the semicircle plus the area of triangle JKL. The area of a semicircle is being a half circle, and the area of a circle is pi r squared. The area of a semicircle is a half pi r squared. The area of a right angle triangle, which this is, will be a half base times height. The radius of the semicircle is half of 12.8, which is 6.4, that's squared, plus a half. The base of the triangle is JL, or it's JK, it doesn't make a difference. The base and the height of a right angle triangle are perpendicular to each other. So one's the base, one's the height. So it's a half times 12.8 times 12.8. And now we can just plug that into the calculator. Area of the shape is 146.26 centimeters squared. Perimeter of the shape that will be JK plus the arc, that arc JL plus LK. The perimeter of the shape is just the distance around the shape. Obviously it doesn't include JL because that's inside the shape. It's the total distance around the shape. JK we know is 12.8. Arc JL is just half the circumference of a circle, which is pi times r, and the radius is 12.8. Sorry, it's 6.4. And LK is the hypotenuse of this right angle triangle. So h squared using Pythagoras' theorem equals 12.8 squared plus 12.8 squared. So h will be the square root of 12.8 squared plus 12.8 squared. So we're just going to leave it like that for now and then just put everything into the calculator. That equals 51.01 centimeters. Diagram shows a box in the shape of a cuboid, also called a rectangular prism. Marla has a straight rod of length 10 centimeters. Show that the rod does not fit completely inside the box. Okay, so we have dimensions: length of 5, breadth of 5, and height of 7. A rod that is 10 centimeters couldn't possibly fit lengthwise because the length is 5. It couldn't fit breadthwise because the breadth is 5. It also couldn't fit height-wise because the height is 7. The only possible way that the rod could fit is diagonally, so on the face from this corner to that corner. Okay, we'd need to work that out first. Or from this corner up to the top corner. Those are the only possible ways that the rod could possibly fit inside the box. So we have to determine what we're calling now x and y. Now, if you look at that triangle at the bottom, this is in fact a right angle triangle. Remember, this is a cuboid or rectangular prism is a rectangle projected in 3 dimensions. So we will take a rectangle, a rectangular face, which clearly has interior angles of 90 degrees, and we just project that in 3 dimensions. So this face over here, this rectangular face at the bottom, if we connect the diagonal of that, we form a right angle triangle. That length and that breadth are perpendicular to each other. So to find x, we use Pythagoras' theorem. X squared is 5 squared plus 5 squared. So that's 25 plus 25, which is 50. So x is the square root of 50 which is approximately 7.07. So clearly the rod would certainly not fit if we just label that AB, those endpoints of the diagonal. That rod would certainly not fit inside the box from A to B because the rod is 10 centimeters. It would extend outside of that box. Likewise, we're going to find Y, X, and 7 are also 90 degrees because X is a horizontal plane and the height 7 is a vertical plane. And a vertical plane and a horizontal plane are perpendicular to each other. So y squared equals h squared plus x squared. That'll be 7 squared plus x squared. Instead of taking 7.07 and squaring it, we know that x squared is 50. So that'll be 49 plus 50. Y squared equals 99. Y is approximately 9.95 centimeters. So again, just label that C, that diagonal AC. The rod couldn't possibly fit from A to C because the rod is 10 centimeters in length and that diagonal AC is only 9.95 centimeters. So the rod does not fit inside the box, and that's how you answer the question. Solid A is made from a cylinder and a hemisphere, both of radius 2 uppercase R. The cylinder has a height 5 uppercase R. Solid B is a cone of radius R, don't have to call it uppercase R, and sloping edge X. The total surface area of solid A is equal to the total surface area of solid B. Okay, this is very similar to a previous question we just did. Again, before we can establish the total surface area of solid A, we are going to first break it up into component solids for which we know the total surface area. So the total surface area, without it going into the explanation again, because we did it in an earlier problem, the total surface area of a hemisphere is 3 pi r squared, and the total surface area of a cylinder is 2 pi r squared plus 2 pi rh. Now, in the context of the problem, solid A, if we just look at the cylinder, we have that bottom circular face. Let's say we were painting the solid A, and we have this curved section over here. We would not be painting the inner circular face because it's inside the shape. So the total surface area for solid A would be 1 pi r squared plus 2 pi h. That's the cylinder. Pi squared plus 2 pi rh. And for the hemisphere, the total surface area of a hemisphere is 3 pi squared, but we need to exclude this inner circular face. So 1 less pi squared is 2 pi r squared. Now the radius of the hemisphere and the cylinder is the same. So that'll be 3 pi r squared plus 2 pi rh. Now, just before we get to solid B, let's just use what we know. The radius, lowercase r as I've called it here, is in fact 2 times uppercase r. So that's 3 pi times 2 uppercase r squared plus 2 pi times twice uppercase r times the height. The height of that cylinder is 5 uppercase r. That's going to be 4 times 3, that's 12 pi r squared plus 5 times 2, 10 times 2 is 20 pi r squared, and that equals 32 pi r squared. This is now the total surface area for A. Total surface area for solid B, this is a straightforward cone, and the total surface area of a cone is pi r squared plus pi squared plus pi rs. Pi r squared, the radius here is uppercase r, so it's pi uppercase r squared plus pi uppercase r, and the slant height is, this x here is your slant height s, so it's pi uppercase r squared plus pi uppercase rx. And now they tell us the total surface area of solid A equals the total surface area of solid B. So 31 pi r squared equals pi rx. We can divide through by r, because the radius is a quantity that can't be negative, right? So it's also not that it can't be negative. Yes, it can't be negative, but it also can't be 0 because it represents the radius of a circle. So we can divide through by r. We know that r is not 0. So 31 pi r equals pi x. We can divide through by pi as well because pi is a non-zero constant. So 31r equals x. And we want the radius in terms of x, so the radius will be x over 31.